Hey guys, and welcome back to the next part of reinforcement learning theory. Today we're talking about the Bellman equations. These come up a lot, especially when you're working with things like Q-learning, and hence this is sort of a natural next step because last time we were here, we were talking about values and Q values. If you don't know what those are, definitely go back and watch the previous episode in this series, or not, up to you. But yeah, that's what we're just gonna go ahead and jump into the Bellman equations. So let me go ahead and erase some of this and start talking about what the Bellman equations are. Essentially, we are going to have two separate Bellman equations, one for value functions and one for Q values. And essentially what they'll do is decompose almost what we've been working on. They'll take we'll build them from the definition of a value and a Q value and decompose the function a little bit to get an interesting equivalence that we can use later down the road for a few algorithms. So let's start off with just value, or maybe I'll start off with just showing you what the Bellman equation is. So we have the value of a certain state on a certain policy is equal to the expected value where A is sampled from policy and the next state is sampled from that distribution. We have R A plus gamma, that's a rough gamma times the value of policy of the next state. Cool. So what does this mean? This is our value, right? The value of a certain state is equal to the reward of that state given the on policy action plus the value of, or the discounted value of the next state. This might or might not be obvious kind of looking at this, but let's kind of get into what this means, and we'll do that by starting out with a derivation. So if we remember just the value of a state given a policy, what is it? It's equal to the expected, we're not even going to do expected. We are just going to do, this will be the value of a state for a given actual trajectory, would be the summation, right? Ooh, I'm not great at drawing the summation. You can probably tell. So starting at t time step equals 0, going to t minus 1, it's the discounted reward summed up, right? So this is essentially like, right, R0 plus gamma R1 plus gamma squared R2, and this goes on, right? I should actually erase this, but this is essentially what this is, right? It's just the summed up discounted rewards, and we are using an infinite horizon discounted rewards sort of thing here. This would be different if you were not discounting your rewards. But yeah, so this is what value is. So how do we go from this right here to this? This is kind of what we want to prove, right? And it's actually not too difficult. What we can do is we can pull out the first reward, right? So let's say value at a certain state of the policy equals the reward at, and we're starting at 0, right? So let's just say the reward is 0, and this would be times gamma to 0, but that's just 1, so we don't have to, we can ignore that, plus the, I'm really bad at these summations. You'll have to deal with it, I guess. And now we're going to start from t1 because we've pulled out the first time step, but we're still going to big T minus 1 of essentially the same thing, gamma of t, r t. Okay, so this isn't too bad, right? We just pulled out the first time step and then we're summing the rest of the time steps. This is a fairly easy conversion. What we want to do next, though, is equals r of 0 plus, we want to pull out a gamma. And the reason we want to do that is because we want this gamma to start from, we want this term to start as 1, and you'll see why in a second. So if we pull out a gamma, what do we get? We get, this is still the same, t equals 1. We just have gamma now here will be to the t minus 1. And r will still be, the reward will still be r to the t. So hopefully this makes sense. It's just some basic sort of algebra right here. Why did we do this though? Why did we transform into this? And what you might notice, and this is actually pretty cool, is, let me draw a sort of divider right here. What's this term right here equal to on the right side? Maybe I should get a different color. This term on the right side right here, what's this equal to? This gamma times, or sorry, let's not include the gamma, just this. And if you're very sort of keen on this, what you might notice is that this is almost the exact same as this right here. Right, so what's the difference here? Well, the difference is we start from t equals 1. However, we do start from gamma where we're subtracting 1 of the t, so these are the same. The reward is just starting one state, sort of one time step later, right? So this is almost equal to this because this is equal to, this specific part is equal to the value of the, I guess, what should we call it? S of t plus 1 is the value of the next state, or sometimes maybe an easier way to call this is just s prime. So if we write this all together now, what we'll get is, let me switch the color again. What we'll get is this whole thing right here, and I'll move over here, equals R0 plus gamma of the value, this policy of the next state. And see what we have here. This is essentially saying, right, if we take a trajectory, a bunch of rewards and actions, and we pull out the first reward, what we see is that the value of the entire trajectory is equal to the reward of the first time step plus the value of the second state. And we can just keep doing this, right? We can keep pulling these rewards out because that's what the value is equal to, right? It's just the summed up discounted rewards. But if you notice, this is actually now very similar to what we have up here when I originally showed you this Bellman equation, right? This Bellman equation is essentially the same thing, right? It's saying this reward at, it's just a little bit more generalized. It's saying the reward with this state action pair plus the value of the next state equals the value from this original state. So the only difference is here we're starting from state 0 or time step 0, whereas here we're starting from a generalized state action pair. But we've essentially, I guess we can't call this fully proven, but I think it's enough to probably convince you guys that this is like a value thing. That's how we kind of ended up with this Bellman equation. We're essentially just pulling the reward out of the first time step and saying, if we take any value, of the value of any state, that is equivalent to the reward of that state plus the value of the next state we end up in. And that's pretty interesting. The reason that's pretty interesting might not be super obvious yet, but this gives us another way, essentially. We've already found one way to do this in one of the previous episodes, but this is another way. Once we actually have data, we can start sort of training a value function, right? Because we now have an estimate for the value function. This is bootstrapped because the value itself, the value is defined by partially the value itself, right? We have the value equals something. We'll actually have a value for this, but it's partially based on itself, which is something we'll get into later. But either way, it's an interesting equality. So this is the first Bellman equation I want to point out. Let me erase this, or most of this, and show you the next Bellman equation. This one will be for Q values, and what you'll notice is that it's very similar. Whoop, whoop, whoop. What color should I use for this one? I'll use a different color. Let's go with, I guess, some blue. Some good old blue. Blue. Looks good. So the next one is the Q value. Let me do that a little bit bigger. Q value on this policy of a state action pair equals the expected value of a state. The next state is sampled from the P distribution. And then we have RSA, same as this so far pretty much, right? Plus the discounted expected value of the next Q value. prime. This, and then add another bracket there. Cool. So what's this? This is almost the same thing, right? It's essentially the equivalent thing for the Q value. We're saying that the Q value at a given state action pair is equal to the reward we get from that state action pair plus the discounted Q value for the next state and action pair, so long as that action is sampled from our policy. Did I write that? I didn't write that. I should write a prime is sampled from the policy or on policy. So this is essentially the same thing. We can actually substitute this whole thing right here. Maybe I'll change colors again to green this time. This whole thing right here is actually just value, right? Or I guess I should say this whole thing, including the expected part right there, is just equal to the value of S prime, right, for this policy, because this is assuming we're on policy. We're sampling an action from the policy. Interesting equivalence. I'm just pointing out just because. But anyway, this is essentially the same thing, right? We're saying the Q value of this current state action pair is equal to the reward times or plus the discounted Q value of the following steps, step. That is really all there is to these Bellman equations. They're actually quite simple so long as you understand the original definitions of value and Q values. One thing I want to sort of give a tip for when you're studying reinforcement learning, especially things like this, is really don't try to I hope you're not trying to remember these two formulas. It's a bit of a waste of time if you're always trying to remember every single formula. There's so many, you're never going to fit them all in your head. I mean, well, I'm sure some people can, but what you should really be understanding is what values are and what Q values are, right? As long as you know that values are the discounted summed reward of a trajectory, or the expected summation of the reward series of that trajectory, and Q values are the same thing except for starting with a different action, you should be able to derive these, right? I just derived these. I didn't have any papers next to me showing that. I just know it because of the fact that I know what values and Q values fundamentally are. So if you are studying this, just a quick tip, please don't try to remember these as is. But yeah, as I just said, I won't repeat it again. So that's really all I have for now. One thing, I guess a last question that I always ask at the end, right, is why are these important? And it's sort of the same reason I mentioned earlier, is these give us a new way to figure out what this Q value should be when we're trying to learn it through a method called bootstrapping, which is where it's equal to itself slightly modified, right? So the Q value is equal to itself modified by the current reward. Because although this is still technically an estimate on the right side here, if we drop the expected value, this is an estimation if we're calculating with real data, right? But it's slightly more accurate. It should be slightly more accurate than this itself because of the fact that we do have an actual reward here. And that's just getting into later when we work with training and real data that actually, when we're working with just the stats, that really, I guess that's not a huge point. But this comes in huge later when we work with things like Q learning. I believe this is important in SARSA too. And lots of big algorithms, even modern day ones, still use this same approach. So definitely keep it in mind. It will come back very shortly. Thank you so much for watching though. If you enjoyed, please like, subscribe. It means a lot to me. And I hope to catch you all next time.